Hello, everybody. A warm welcome from my point of view, and good morning, good evening, have a good night, or whatever, where you are coming or where you're sitting. So I'm happy to see all of you here. So we now have 30 participants, but we are expecting more than 100, as Natalie told us. So welcome to our workshop. My name is Martin Dameres, who is not knowing me. I'm a member of the Ozone CCI project team, and I'm also acting as a contact person for the Climate Modeler user group, but also I am the lead of the climate research group in the project. So I'm working at the German Aerospace Center, Institute of Atmospheric Physics, and in the Department of Earth System Modeling. But before say some words about the workshop and why we are here, I would like to hand over to Christian Recher from ESA to welcome all of you on behalf of ESA. So Christian, it's your floor.
Yeah, thank you, Martin. My name is Christian Recher. I'm the technical officer of this Ozone CCI activity, so representative of ESA. I usually work in Esrin. I'm also taking care of another CCI project, greenhouse gases. Yeah, I'm very happy to welcome you. There's so many people already online, and more will be coming. And I'm very much looking forward to the presentations that are being lined up, and also hope that we have fruitful discussions after that. So welcome again from side of ESA.
Yeah, thank you, Christian. Yeah, to say some introductory work about the workshop and the project itself. So in the last years, so I look back, and it's about more than 10 years we are working in this project. So we had a lot of discussions, in particular in connection with our project, about the user requirements and the respective ozone data products, and together with the group of data production. And therefore today I'm really happy that many members of the project are here, and that some of them will be available and will be able to present excellent results of the project, and to present the results of our work in the project. And they have more or less produced jointly in the project, and this is really a success story. So from my point of view, these data products, which are based on the European satellite instruments mainly, they all have very high quality. And tomorrow, so today we will get an overview about the let's say the data products of the project we have produced. But tomorrow we will have some selected invited presentations in addition, which will deal with the scientific use of these data sets and illustrating also the potential of these data sets. And at the end of the workshop tomorrow, we will have a lot of time for discussions where you, the participants of the workshop, can more or less share your opinions, raise questions, express wishes for future and further actions. So which products you are looking for, which other essential climate variables should be analyzed in combination with these new ozone data sets, and what else are you missing? So you can see that there are many points and questions raised, in particular for the discussion tomorrow. And this is where I'm looking forward. So now I wish you all a very interesting workshop, stimulating talks and fruitful discussions today afternoon and also tomorrow in particular. And now I would like to hand over to Michel. Michel van Roosendaal is the leader or coordinator of the project, and he will give you some more details of the project itself and the products. Thank you.
Thank you, Martin, for the introduction. So I would like to join you and Christian to welcome everybody to this very exciting Ozone CCI user workshop. And before we really go into the details and into the main body of the workshop, I would like to give a very short introduction to basically the context. I guess you all have an idea of what is. Okay. Okay, sorry, there was a misunderstanding about who should share the presentation. Sorry. you all have an idea about what is CCI. Let me just share. Okay. Okay. Do you see something?
Yes, we do, but not in the old school.
Oh, it's fine.
It's fine.
Yes. Yeah.
Okay. So sorry again for this. So yeah, what is CCI? So I guess you all have an idea or a rough idea, but maybe to make things a little bit more clear, the Climate Change Initiative is a large-scale program from the European Space Agency, which was developed over the last decades with the ambition to provide a response to the needs of the international user community for high-quality data and information about climate change. And as you can see on this picture, which is basically representing the overall program just in one slide, the CCI program is addressing a large number of essential climate variables. At the moment, 21 variables are addressed by the program, and this is concerning oceanic, terrestrial, and atmospheric domains. And you can see that ozone is only one variable around in this large context of the ozone of the Climate Change Initiative program. So, okay, I try to. Okay. So the CCI program was started about 1 decade ago, exactly in 2009. And we are currently already in the second phase, actually in the middle of the second phase of the CCI program called CCI Plus program. But only 5 years after the start of the CCI program, the European Commission launched another climate-related program in the framework of the Copernicus program, called the Copernicus Climate Change Service, or C3S, that you certainly also heard about. And this program is led by ECMWF. And immediately when this initiative was taken, discussions were started to establish a partnership between ESA, CCI, and ECMWF leading the C3S. And this led quickly to the formulation of a cooperation agreement between ESA, CCI, and C3S on a number of aspects of provision of climate data records, coordination, and R&D activities, and collaboration on pre-operational developments. And you can see that the Copernicus program is actually containing 6 services, and climate change is one of these services. So this cooperation agreement has led, after 5 years of operation, into a nice collaboration, which is addressing several aspects. But I would say that basically the fundamental idea behind the collaboration, or the way the collaboration is organized, is that CCI is providing the pre-operational framework where developments to generate climate services, and especially climate variables, is performed. And the idea is this that once these services or products are becoming mature enough, they are transferred to the C3S to become operationally produced. And actually, this idea has been very successful, since about 16 ECV have been, in the meantime, transferred from CCI and uptaken into C3S, as you can see in the figure here. And ozone is again one of these variables which were transferred. So this explains that actually the access to the ozone data has in fact 2 main entry points, and one is at the level of the CCI program, and you can see the link which is indicated there, and there you go directly. You can access the product which are stored on an FTP database accessible from the from the Ozone CCI webpage under the data tab. And there is another entry point, which is located at the Copernicus Climate Data Store. And there you can also access data through the Copernicus service. So the Copernicus service is the operational service. It has a strong focus on delivering, I would say, major level 3 data products, while the CCI is producing, I would say, the corresponding level 2 data and also data which are more in a development stage or less mature than the data that are provided on the C2S. So yeah, this was just a very short introduction to give you a framework. What is CCI? What is C2S? In which way do these organizations work in collaboration or in cooperation? So the objective for this workshop, this was already introduced by Martin, but to come back again, today we will essentially present the Ozone data product that were developed within CCS and delivered or produced operationally in C2S. And tomorrow we will more give the floor to the scientific user community, listen to interesting applications, and see a little bit all these data are fitting into the scientific context. And so, of course, we expect that we will have some discussions, interesting discussions, get feedback from the users on the usefulness of our data product, but also where are the gaps, what are the wishes or critics or ideas, whatever we can get out from these discussions. And we hope that this will give us some inspiration to better define the future activities in future CCI phases that we expect for the next years. So yeah, this is all for my introduction. And before we move into the actual workshop, I just would like to remind a few practical aspects. So we have planned for the different slots, 20 minutes in total for each presentation, which means 15 minutes for the talk, 5 minutes for questions, and we will give a warning 1 minute before the end. So when you want to ask questions, please use the chat to enter your questions, and also please, because we are quite a lot of people now on the WebEx, don't activate your webcam unless you want to say something. So thanks a lot for your attention. And now I think I can give the floor again to Martin to introduce the first session of this workshop.
Yeah, thank you, Michel. Yeah, this is now brings me to the first part of the meeting of the workshop. So we will start with a session about the nadir sensors, and I will hand over now to Diego Loyola and to Michel again, who will chair this session. So, Diego, are you there?
Hi, Martin. Thank you for the introduction and welcome everyone. So we will have 4 presentations, 2 dedicated to total ozone and the other 2 to ozone profiles. Let's start with the total ozone. The first presenter is Melanie from DLR. So Melanie, please.
Yes, hello everyone. Can you hear me?
Yes.
Everything is fine.
Okay. I will try to share my screen.
Yes. Now it is there.
Okay, fine. Do you see it full screen?
Not full screen.
No. No.
So now the presentation we can see, but not full screen.
Okay, I'm sorry. I do not know why this is not working.
Melanie, do you have animations?
Now it is there. Now it is full screen.
Oh, okay, thank you.
Very
Now
Okay.
full screen is there.
Hello again.
Thank you. You can say.
Okay.
Yeah.
As already introduced, I would like to present the total column climate data record developed as part of CCI Plus, called GOM type Total Ozone Essential Climate Variable, GTOECV. And this level 3 data record is generated by our team at DLR Oberpfaffenhofen, and the underlying level 2 processing is performed by the colleagues from BERA. In the introduction, I will give a brief overview of the satellite sensors that are included in GTOECV. I will present the main features of the level 2 retrieval algorithm GODFIT and the merging approach, and finally show some science.
Melanie, I cannot hear you. Can you hear me?
I don't hear Melanie either, and I do hear you, Martin.
Okay, thank you. So I think Melanie has a problem with the line.
She has the presenter role, she has everything, she has all the rights.
She probably doesn't know that we can't hear or see her. She's probably given the talk.
No, I don't think so, because I don't see any change in the slides.
Yeah.
It looks like the connection is broken.
Maybe she should. Oh. She's
I
Melanie,
guess
we can't hear you. We can see your second or so slide and your pointer, but we cannot hear you.
it's moving.
Natalie, I think you can just start sharing your screen yourself, and then it will take away her screen, and then she will realize something is wrong.
Okay.
Good idea. You can stop sharing for me.
So I gave her the presenter privileges again. I don't see anything happening.
I suggest to continue with the second presentation.
The second
and
presentation.
Try to
Yeah, I
sort
agree.
out the
I
problem.
agree. Good idea,
So-
Diego.
Yeah.
Okay, so hi, it's Katerina. I think it's my turn. Can you hear me?
Yes.
Okay, great. Can I share my screen, Natalie?
Please do it.
Okay. So you should see.
Yes,
my
yes, it's fine. It's full
presentation
screen.
now.
Everything is fine. Thank you.
Great, great, great. Hi. Hi, so my name is Katerina Garanea from the Aristotle University of Thessaloniki, and I will present the quality assessment results of the total ozone products retrieved within this project. This is my outline. First of all, I'm going to present you the level 2 validation results. The validation was done with respect to ground-based measurements from Brewer and Dobson instruments. And they were 7 sensors were validated, as you can see here, along with Tropomi, which was processed not with Cockpit version 4, which is the official algorithm of this project, but with its own, but almost the same algorithm. And I will show you some few plots, a few graphs of a new methodology that will be applied here too for the study of the combined ex-ante uncertainties for satellite and ground-based measurements. And going to level 3, I'm going to show you the validation results with respect to ground-based total ozone columns 2 and the consistency check using SBUV version 8.6 merged data. Before going to the validation results, this is a map of the spatial distribution of the ground-based stations used in this work. As you see, we use 60 Dobson instruments that cover both hemispheres and 52 brewers from the northern hemisphere only. And going to the level 2 validation results, of course, I would like to thank Christophe Leroux and the BIRA team for the data. And in this table, you see all the satellite data processed with Cockpit version 4 and their temporal coverage, which is 16 years maximum for GOMI and OMI. The newest sensor is GOMI 2C that was launched in late 2018. And since Tropomi is already integrated in the GTO ECV dataset, we will also see some validation results covering the time period of each operation. These are the validation results of all 7 sensors processed with Cockpit version 4 with respect to brewers. These are the percentage differences of the 2 sources of data in the form of histograms. They all have a normal distribution around their mean difference, as you see, which for the Northern Hemisphere ranges between 0.8 and for GOMI and 1.7 for GOMI 2B. The correlation coefficients of the comparisons are always above 0.98, showing a very good agreement between satellite and ground-based instruments. And the mean standard deviation is always less than 3.5%. Of course, we have to keep in mind that this includes any collocation mismatch and the ground-based measurements uncertainty. Here you see the time series of the percentage differences of the comparisons for all 7 sensors and Dobson and Brewer ground-based instruments, Dobson for both hemispheres and Brewer for the northern hemisphere only. In the table, there are some statistics for the mean biases and the mean standard deviations of the monthly mean time series for both hemispheres. And as you can see, we have a very nice consistency between the sensors. The differences in mean relative bias and mean standard deviations is less than 1% in any case. This is the seasonality plot, the seasonality variation for the brewer comparisons. And in the table, you can see the respective peak-to-peak seasonality for each sensor. The product requirement for the seasonal cycle of these products is 3%. Therefore, they are all well within the requirements. And furthermore, I would also like to mention here that we are already working on the effective temperature correction of the Dobson ground-based measurements so as to minimize their enhanced seasonality as well. The effect of other influence quantities on the comparisons are also studied. And here are the dependencies on solar zenith angle, effective temperature, ghost ozone, and cloud fraction. I just chose some indicative plots to show you here. For solar zenith angles below 80 degrees, sorry, the dependence on this variable is as expected, up to 3% for schemaki. This is the highest dependency we see. And the dependence on effective temperature goes up to 2% also for schemaki. And of course, as you can see, no dependency at all for ghost ozone, cloud fraction, or other influence quantities that are studied. Here are the respective plots for the Tropomi validation results, the time series, the monthly mean time series, where only common collocations to Tropomi are shown, which means that we go from late 2017 onwards. Here you see some statistics for the Tropomi total ozone column, the offline total ozone column. As you can see, we have a very small mean bias, positive but very small, 0.5%. The mean standard deviation is 2.6%, and the peak-to-peak seasonality 1.6%. We have a very nice consistency of troponin to the other sensors, and the difference in the mean relative bias is negative. You can see here that the orange symbols are always below the others. But it's very small. It's goes up to 1%, and the mean standard deviation is smaller, of course, for troponin as well. And the seasonality is almost the same to the others, except for GOMI2A, which here, where we zoom in to the time series, you can see that GOMI2A has some issues for the last couple of years when it is switched to a solar model because it's losing the solar visibility from time to time. And here we see the pole-to-pole graphs showing the collocations of its sensor, averaged in 10 degrees latitude bands. Over the overall agreement is very good in the Northern Hemisphere, and no particular dependence on latitude is seen. In Southern Hemisphere high latitudes, the dependence is mainly due to the ground-based measurements. And we see that we have a nice consistency of troponin to the other sensors, with the differences up to 2% with respect to OMI and GOMI2D in the Northern Hemisphere. This slide is the work of my colleague Tyler Verhurst from BIRA, who applied methodology using the chi-square test to investigate whether the satellite and ground-based data agreed within their combined uncertainty. This is a methodology that uses the reported uncertainties of both sources of measurement and helps us examine whether they represent the true ozone values. The upper left panel is the time series of the troponin and the collocated Dobson ozone for Brisbane, each with its ex-ante uncertainty estimate shown as error bars. And below we see the time series of the absolute differences, which are first of all corrected, bias corrected, which means that the mean bias of the differences is subtracted. And then they are normalized by the combined ex-ante uncertainty. So this K factor should mostly fall below 1. Some data points are allowed to be between 1 and 2, and a few others may fall between 2 and 3. But the total number of points below 3 for a normal distribution should be 99.7% of the dataset. So for this case, we can already see that the satellite and ground-based datasets for Brisbane agree with each other. And the reduced chi-square, which is calculated using the formula you see here, puts this information into a single number for each station. The value around 1 is ideal, as it is in the case of Brisbane, as you see here, it's 1.3. And below in the histogram, you see the reduced chi-squares for the entire ground-based network used by my colleagues at BIRA to validate the troponin total ozone columns. Most stations have excellent chi-squares around 1. Only one has a chi-square of 3, but this is probably a ground-based data quality issue. So this is a methodology applied to troponin data, but it will be extended to other datasets within this project. Moving to the level 3 validation results, of course, I would like to thank Melanie for the data. Some information on how this comparison was applied. First of all, in order to create the level 3 field from the good ground-based stations, all stations that we routinely use in our validation chain were gridded into the same 1-by-1 boxes on a monthly basis, and only direct sun ground-based measurements were used to achieve the best quality. And the lower limit of 10 points per monthly mean was enforced. And additionally, in order to compare level 3 and level 2 validation results, the time periods for the level 2 data were used as you see in the table. As you can see, Gomi and Skiamaki are used up to 2004, and then Omi takes over Gomi 2A in 2007, and so on. Finally, a latitudinal seasonal constraint on level 2 data was also enforced, as Melanie does in her work. According to this table that you see here, we have some latitude belts with, that are allowed to contribute in our validation for each month. And in this plot here, you see the time series of the two data sets, the ground in blue symbols and the level 3 data set in red symbols for the Northern Hemisphere only, that is, and compared to Brewer ground-based measurements. So in the monthly mean time series plots for both hemispheres and compared to Brewer and Dobson, these are the percentage differences to ground-based measurements. You see that we also plot the level 2 data from the 6 sensors that are used to retrieve the level 3 data set. The level 3 mean biases are 0.5 to 1.3% for the Northern Hemisphere and 2% for the Southern Hemisphere. The mean standard deviation is less than 3% in both hemispheres. And except for a small number of outliers, we can say that the overall agreement between the level 3 and level 2 datasets is within 1%. In the Brewer comparisons, we see that the level 3 seasonality is up to 1.5% peak-to-peak, being much lower than that onwards since 2004, when OMI was introduced into the dataset, probably due to its better sampling. And in this table, the statistical analysis of the level 3 and level 2 comparisons is shown in terms of drift per decade. As you can see, the level 3 drift for the collocations in both hemispheres and with both types of ground-based instruments is within the requirements, which is 1 to 3% per decade, which is also the case for the level 2 datasets from the 3 sensors that have a long enough time series contributing to level 3. Of course, we could not examine Skiamaki or Tropomi because they have a rather limited time series. As for the respective pole-to-pole graphs shown here, we see that the level 3 product doesn't have a different dependence on latitude, and it agrees within 1 to 2% with the level 2 datasets for most of the latitude bins. Finally, a consistency check was performed using the SBUV version 8.6 merged data from NASA, shown with black lines and symbols in this plot. The time series in both hemispheres are in very good agreement, within 0.5% in the Northern Hemisphere and 1.3% in the Southern Hemisphere. The seasonality with respect to Brewer ground-based measurements is very similar for both datasets. And the drift per decade for the level 3, which is shown in the table below, is comparable to the one that results from the SBUV statistical analysis. So going to my conclusions, for the level 2 validation results, we saw the results for 7 sensors processed with CodeKit version 4 and Tropomi offline total ozone column product with respect to Brewer and Dobson ground-based measurements from wood. The correlation coefficient was very nice, always above 0.98. The intercessor consistency was very high in terms of seasonality and mean bias. And we saw no unexpected dependencies on influence quantities. In terms of statistics, I will not repeat myself. They were all within the product requirements, as we saw. And we introduced a methodology that will be applied here as well for the combined ex-ante uncertainties. As for the level 3, GTO-ECV dataset for 25.5 years. The mean bias of the comparisons with respect to ground-based data was always less than 2%. Very small drifts were detected, plus minus 0.5% per decade. And we have a very nice agreement of level 2 total ozone columns and SBUV to level 3 within 1%. So as a result, we can say that level 2 and level 3 GTO-ECV products fulfill the requirements for long-term stability, and therefore they are suitable and very useful for long-term analysis of the ozone layer and for simulation applications. That's all from me. Thank you.
Thank you very much, Katrina. We have time for a few questions.
Okay,
so
yeah.
we have a question from Irina. Irina, will you formulate your question, please?
Hey, can you hear me?
Yes.
Yeah.
Oh,
yes.
thank you. So I was just curious, you had a plot 2018 through maybe 2020, where you're comparing probably level 2. The first half of presentation.
Okay, let me go back.
Oh, yeah, we just missed it. No, go back, go forward
for
now.
Tropomi, you mean? This one?
Yes, with Tropomi.
Okay.
But it's not just Tropomi. I'm just looking at this 2000, but very sharp bias in the probably 1 month, right? At the end of this.
What do you mean in the northern hemisphere or in the southern hemisphere?
Oh, sorry, it's for the southern hemisphere.
Southern hemisphere. You know, the thing with the southern hemisphere is that we mostly look at a consistency between the sensors because the ground-based stations over there are not very dense. And the quality of the data is not always the best. You see here at the end of the data sets, the time series, if I restrict this plot to minus 50 degrees, these will go away, which means that they come from a station that is close to the pole, and they are probably not very quality controlled, but still we have to use some of these measurements because we don't have many to choose from.
Yeah, but I would just worry about that if some stations report or get not reported the data, then you might change the mean latitude. Basically, maybe you need to can you look into the what's your average latitude when you combine these stations, just to make sure that you're
that's why I use these plots to verify my results, where you can see that we can see that we have in this latitude bin we usually have a station that reports low total ozone columns, but we don't have many to choose from. You know, this is a really difficult situation when you have to have a global ground-based validation. So sometimes you have to keep a station that reports not so quality controlled data just to have something.
All right, yeah.
Yeah,
and I hope the 2020 data were available. Yeah,
sorry?
Well, I just didn't know how 2020 data were available. I mean, all of them were available, I guess, for the 2020.
Yeah.
So I suggest to continue with 2 more questions. The next one is William. Maybe you can formulate your question.
Yeah, sure. No, I was just interested in the plot you showed at the end with the SBUV and the level 3 data.
Okay, let me go there. Sorry. Yeah.
Now I recognize that there are it's very small changes, but I've been doing some trend analysis on these 2 data sets, and I've noticed a drift of 1 to 2 Dobson units in them, and it sort of looks like there's a downward drift going on in SBUV or an upward drift in the GTO in the last sort of 3 to 4 years. Am I just imagining it? Or do you know of anything that might be causing a drift to go on?
Well, to tell you the truth, I cannot talk for the SBUV dataset because we are only using it here just to confirm the quality of the GTO-ECV dataset. And as for the possible drift that you could see if you look just into some years, the later years, I think that this may be caused by many factors, probably the number of sensors that contribute for this time period, and it would be very useful if we all could hear what Melanie has to say before my presentation, because there are some things that I would really like to see so as well. So no, I'm not in the position to say what is the situation for some particular years, but I can look at the general picture and see that the picture is it's rather good.
Okay, that's fair. That's
yeah,
a fair.
I also see. Sorry, I also see this part of the dataset here, which looks weird to me, and it's something that I am going to discuss with Melanie. Of course, we didn't have time to talk about this before the presentation.
I appreciate the answer, Catherine. Stacey's just added something to the chat, saying that N19 in the SPV data begins a small drift around 2016 as the orbit drift begins to accelerate.
Sorry, I did not understand that. Can you?
On the chat, Stacey has said that there's a small drift in one of the satellites that contributes to SPV after 2016. I obviously there's a short time here, so I might communicate with her and you offline.
Okay, so you mean about this one that you could possibly? Yeah. Okay, yeah. Yes, okay, this has to be looked carefully into. Yeah.
So last question before we need to continue. So the next question is from Paul. Paul, please.
Yeah, I think I got an answer from Wolfgang though. The difference in the ozone cross sections.
Okay, then thank everyone. Let's try again with Melanie. So I will show the slides and Melanie will present them. So let's see if it's working now. Can you see my screen?
Yes, it is now there.
It's okay. Melanie, please. We cannot hear you, Melanie. That's a problem when we rely on the internet and the connection is not working.
Okay, can you hear me now? This is Melanie.
Now, yes, please.
Oh, I'm very sorry about the internet connection suddenly collapsed. Okay, I will try again. Okay, I will present the total ozone column record. And in the introduction, I will give a brief overview of the satellite sensors that are included in GTOECV. I will present the main features of level 2, algorithm Godfit, and the merging approach. And finally, show some science highlights that focus on the possible applications of GTO. Next, please. Okay, the analysis of atmospheric ozone is quite important due to its strong link to the Earth's climate and its influence on the radiative budget in both the stratosphere as well as the troposphere. And the Ozone project focuses on the generation of multi-decadal time series of harmonized and consistent ozone data from various types of satellite sensors. Next, please. The main science question is the assessment of long-term changes, in particular monitoring the effectiveness of the Montreal Protocol. Do we already see signs of recovery? And the investigation of interannual variability, which has a major impact in middle and high latitudes, as can be seen in the plot taken from the last WMO report, which shows total ozone as a function of time for different latitude belts. The development of the merged total ozone record started more than 10 years ago now as part of the first phase of ESA Ozone CCI. The satellite sensors that are included measure in nadir viewing geometry and cover the UV visible and near infrared spectral range. The merged data record starts with GOME on board ERS-2 in 1995, which provided measurements until 2011, followed by Skiamaki on board Envisat from 2002 to 12. The first version of GTOECV included also observations from GOME-2 METOP A. Next, please. And in the second version, from the second phase of CCI, OMI and GOM2B have been added. Next, please. The current version, which I will present today, generated in CCI+, includes also TROPOMI Sentinel-5P data. Furthermore, part of CCI but not included in GTOECV are observations from OMPS, SOMI NPP, and GOM2 METOP-C data. As you can see, the overlap periods of the sensors are quite long, in general more than 5 years, except for TROPOMI, which is a very good prerequisite for the homogenization of the data. This table here summarizes the main characteristics of the individual sensors, and I would like to draw your attention to the quantities which define sampling. In the course of time, the ground pixel size significantly decreased from 320 times 40 square kilometers for GOM to 3.5 by 3.5 square kilometer for TROPOMI. We have global coverage every 6 days for Skiamaki and daily for TROPOMI. The swath varies from 960 to 2,600 kilometers. And equator crossing for OMI and TROPOMI is in the early afternoon and in the morning for GOM, GOM2 and Skiamaki. But for the total ozone, this difference should not play a major role. Next, please. For illustration, these two plots show the daily coverage of GOM in 97 on the left compared to TROPOMI in 2020. And although ozone does not have such small-scale structures as, for example, NO2 or SO2, nevertheless, one can easily see the improvement achieved with TROPOMI. This difference in spatial and temporal sampling has a significant impact on the representativeness of the monthly means, which we generate in CCI, and this should be kept in mind when comparing our data with either highly resolved model data or sparse ground-based measurements. Next, please. An important aspect and advantage of GTO is that all underlying total ozone level 2 datasets are processed with the same retrieval algorithm, which is Gottfried version 4. Detailed information can be found in Leroux et al. 2014. Gottfried has been continuously developed for the last 15 years and it is very mature. On top of that, it is used for operational TROPOMI offline processing of total ozone. Ozone is retrieved in the Huggins bands and Gottfried is a direct fitting approach, which means that simulated spectra are directly adjusted to the observations. The wavelength dependence of the light path is taken into account. Compared to DORS, the retrieval is more accurate for large optical depths, but on the other hand, it is much more computationally demanding. Next, please. Ozone cross-sections come from Serdyuchenko et al. And a priori ozone profiles for the stratosphere are taken from the Labo total column classified climatology. Additional information for the troposphere comes from OMI MLS. As part of the fit, the temperature profile is adjusted. The spectra are corrected to account for polarization and inelastic scattering, and an effective albedo is retrieved simultaneously to ozone. In order to enhance or optimize intersensor consistency, an additional soft calibration is applied to Skiamaki and GOM2 level 1 input data. Next, please. Now I would like to introduce the homogenization approach. Although the intersensor consistency of the level 2 data is already quite high, small differences remain, which we further reduce before merging the records using a straightforward method. We use one instrument as a reference and apply correction factors to the others. And because of its remarkable long-term stability and the long overlap periods, OMI is selected as our reference sensor. The plots show the relative difference as a function of latitude and time for the individual sensors with respect to OMI. And the adjustments which we apply take into account the latitudinal dependence of the differences. And for OMI and Skiamaki and TROPOMI, the correction is constant in time, except for a seasonal dependence. But for GOM2A and B, we additionally correct for a small long-term drift in the difference. Next, please. On the right-hand side, you see in the bottom panel the difference for TROPOMI before the adjustment, and in the panel above TROPOMI versus OMI with the correction applied. Next, please. The correction is applied to daily gridded data, and then we average all available daily data and finally compute the monthly needs. In the final record, GOM and Skiamaki are included until December 2004. At the moment, GTOECV covers the 25-year period from July 1995 to December 2020. The spatial resolution is 1 by 1 degree, and we provide ozone monthly means, standard deviation, standard error, and the number of measurements. More detailed information can be found in these two AMT papers. Next, okay, just a few examples. 2015, total ozone in the top row and corresponding standard deviation in the bottom row. We see typical ozone features, high values in April in the northern hemisphere and extremely low ozone in October in high southern latitudes. The standard deviation is quite small in the tropical region and increases toward the poles. Next, please. As you can see, there's some white space where no data is provided, and the UV-Vis sensors do not cover the polar night, and therefore we apply latitude thresholds in order to ensure good representativeness of our monthly means. Next, please. In the last part of my talk, I would like to show you some science highlights regarding GTOECV. Already from the beginning, more than 10 years ago now, it has been used for comparison with models and for the evaluation. On the left, results from 2009, seasonal mean ozone from GTOECV in the top row and chemistry climate model data in the bottom row. On the right-hand side, a more recent study by Chipperfield et al. Who
Melanie, I think we lost again the connection.
I can't hear her either.
Melanie? I will try to finalize this presentation, otherwise it's becoming too problematic. So on the right, you see here more results, more recent papers. On the left side, you see comparisons with the data from NASA, the MERA2 data. Tomorrow there will be a dedicated presentation about that. On the right side, you see also the comparisons that are part of the ACP paper from MacBeva 2018, where several data sets were compared from nadir sensors and also ground-based measurements. And other very interesting result is also the provision of regional ozone trends. That's, I think, one of the strengths of this data set. We can provide these regional trends on 1-by-1 resolution. Applying the usual proxies as solar cycle, QBO, and ENSO index. And based on that, also we can provide, again, on a regional scale, what's the time needed for measurements so that we can really detect some trends. As expected in the equatorial regions, we will need more data, maybe to 2040, but for high latitudes already now, I think the trends are quite stable from the statistical point of view. The last part is a very recent paper published by Martin and colleagues, where we compare tropomic data with GTO data for these two episodes, especially the 2020 Antarctic low record ozones and the 2020 Antarctic conditions, where I think there will be also more presentations tomorrow going into more detail here. So the summary, so this data already covers 2.5 decades with using UV sensors and homogeneous data set. You already saw the validation by Katerina. That has been used in the BMO assessment since 2010, and also is used continually in the BAMS assessments since 2014. And as already explained at the beginning, the data is provided operationally by CCI and also as part of the C3S project. Thank you. So let's move now to the question side. So as I was presenting, I was not able to look at the chat. So
Yes, I'm not completely sure where the questions shift from one presentation to the other. There was a question about why OMPS is not used, I think.
What about OMPS and then from Paul Newman?
This was from Paul Newman. What about OMPS? Maybe you can answer.
Yeah, we are comparing the data with OMPS, and we also, as part of the activities plan, as still part of CCI, we will also try to extend back in time, so merging also with the NASA data set. So that's in the plan.
Yes, Paul, if you want to say something more, please don't hesitate to to intervene.
That answers my question. I think Katarina's talk showed the comparison. So I'm guessing this is just for God fit total ozone.
Yes, I guess that's the answer. Okay, so there is a question from Arno Keppens. Would you have any news on the development of the merged GPO or GOP-ECB for nadir ozone profiles?
That's a good question. So the idea is to use the same strategy for merging the nadir ozone profiles, and we plan to do that also using the total ozone as an extra constraint. This work is just started in the CCI project. The plan is that in around 1 year from now, this will be available. So also a merge ozone profile for nadir.
Okay, there is a question from Irina concerning the regional trends, whether they are published.
Yes, the paper from Melanie from some years ago, that's the last publication. We are now working on a new paper, including also the new data.
And then there is a question from Sophie Godin. I think she is asking whether other ground-based instruments than Brewer and Dobson are used for validation.
That's probably a question for Katrina.
That's more a question for Katrina.
Sorry, I didn't. I was distracted by something. Can you repeat, Michel?
Yes, Sophie was asking whether comparisons with other ground-based instruments than Dobson and Brewer are being done.
Yes, not by myself, not by our validation chain, but I'm sure Tile is also validating those datasets with South instruments, I think. Maybe
Yeah,
Tile is
that's
on the line.
correct.
Yeah.
That's correct, yeah. And that's especially interesting for the level 4 MSR product, which is soft calibrated to Brewer measurements. So the South data are really fully independent. So yes, we use those.
Yes, and of course for the vertically resolved data products, there are a lot more ground-based instruments that are used for validation, including LiDAR. But this will come later.
Yes, of course.
Okay, I think we don't have more questions, and we also lost some time with this technical problem. So I suggest to continue now with the profile part. So Richard, you will start with the whole presentation.
Yes, can you hear me okay?
Yes.
Good. And I should try and share my presentation. Okay, you see that?
Yes.
Okay, so sorry.
It's
just
fine.
go on.
Yeah. Okay. Okay. So I'm going to give an overview of the ozone profiles from nadir sensors, and so that work is sort of divided into two. So there's basically the work that we mainly do at REL on retrievals from the UV sensors, and then work on ERZ retrievals, which is being led in CCI at the moment by Catherine Westbez. So I'll go through out the slides on the UV sensors, and then I have some slides from Catherine as well. I think Catherine will join the meeting, but she can't be here right now, so she'll be around later, maybe if there are really detailed questions, but I'll do my best to cover the ERZ part as well in this presentation. So first, a quick run through of the nadir ozone profiles from UV sensors. So yeah, it's a scheme that's been developed over the course of quite a few many years at REL, partly through UK national funding in the National Centre for Earth Observation in the UK, and partly through the first and second ESA CCI projects. So it basically, it produces ozone profiles from nadir UV sensors. The algorithm produces around 5 degrees of freedom for the profile, spanning troposphere and stratosphere. So the algorithm that we use works in kind of two distinct steps, which exploit the different information in the Hartley and Huggins bands, and we do have some sort of emphasis on tropospheric ozone, which comes from a very kind of attempt to really fit in great detail the Huggins band's temperature dependent structure. So over the years, through our involvement in CCI and now in C3S, we've been generating multi-year data sets from GOME, GOME2, Skiamaki, and OMI. And okay, the current work in the CCI program, which is in the CCI Plus project, is not so much on those heritage sensors, but about extending the scheme to Sentinel-5 precursor and the latest METOP-C instrument, and then to investigate the potential to add more information by combining with different spectral ranges. Okay, the algorithm that we have developed here is also basically the basis for the upcoming Sentinels 4 and 5 as well. Okay, so I'm just going to give some, quick overview of highlights and things. So, this is a slide produced by Gordon Labau during the COS-AC VC tropospheric ozone kind of comparison exercise from a couple of years ago, just to sort of illustrate the sort of where we've the kind of general spatial structures that we can see in tropospheric ozone from our scheme, and how that lines up against other products that are out there. So this is a particular month, July 2018. Into this exercise, we actually provided 3 products, a GOME product, which from the nadir profile UV algorithm. We actually provided the ERZ product as well, and an OMI product, which are quite similar amongst themselves. So you can see the GOME product and the ERZ product derived from completely different spectral ranges, but being quite self-consistent. And then that in this slide they're compared to other contributing algorithms to this exercise. So we have the Latmos ERZ algorithm, which we'll come to later, the main CCI ERZ algorithm here. Then there's a LIM MLS OMI combination via a model, this BASCO algorithm, HOMPS tropospheric ozone, and another OMI only algorithm from Harvard. So I think there was a reasonable degree of correspondence between these things, but obviously there are differences, and you have to look quite carefully into the different vertical sensitivities of the algorithms to understand some of those differences. But we stacked up reasonably well in this first initial comparison, and then this will continue. Then just to look at the data in another way. So these show Hofmuller plots for GOME1, OMI, and GOME2. So these are time series that were produced basically at the end of the second CCI main project, where we managed to achieve some reasonable consistency between the different instruments and a reasonable level of stability. So we're showing here the GOME1 time series. Then this is showing actually CAM's model resampled like it should be seen by OMI. Then this is actually the OMI retrieval, and here we have GOME2. So while there are a lot of similarities, there are definitely some differences. And GOME2 and OMI datasets are now extended not in CCI but via C3S. up until the end of near the end of 2020. So this is basically the sort of status of data that can be used right now. But I mean, I think it's clear there are some instrumental issues that affect the stability of this kind of tropospheric ozone, which is quite difficult to do. Some of these we know. So with changes in the swath of GOEM 2, these gaps are due to tape recorder failure of GOEM 1. But there are other instrument issues ongoing, which cause subtle or even not so subtle variations over time. So currently we're kind of at around the 5 Dobson unit level in terms of stability going through these time series. And yeah, work is ongoing, although it's outside CCI now, to produce improved records. So yeah, basically these data sets were what we ended being able to feed into TOR, the first IGAC TOR exercise, and now we are now working on improved data sets to try and iron out the instrumental issues in these time series and hopefully feed that into the second exercise. So okay, nevertheless, the data's has a decent quality, especially when it comes to looking at kind of processes in the atmosphere. So we've quite a few papers starting to kind of emerge from the data, and these are just a few very recent papers looking at things like biomass burning over Southeast Asia, biomass burning over South America, looking at characterizing seasonal and geographical variability by comparison to basically climate models, and also we have a very recent one just accepted for publication on looking at particular mechanisms in the UK chemistry and aerosol kind of climate model representation, in which the data was kind of shown to kind of help diagnose issues in the vertical structure in the troposphere versus the lower stratosphere of the troposphere that were not so easy to address just by the kind of only MLS column alone. Okay, so I'll just move on quickly to new work in CCI Plus. So one of the main things there is to get the scheme working for S5P. That's actually proved to be quite challenging. So there is not yet an operational algorithm for ozone or product for ozone profile coming out of S5P, although that should be released quite soon. Our algorithm, or our attempts to apply our algorithm to S5P have been affected, like the operational scheme, by radiometric calibration issues in the UV that we've kind of tried to find ways of dealing with. So we end up having to fit both multiplicative and kind of additive stray-light type contributions as radiometric corrections. That's now producing reasonable results, but there's still work ongoing to kind of address the remaining biases in the retrievals for S5P. But okay, this is just illustrating sort of current status, which illustrating sort of the retrieved subcolumn in the troposphere 0 to 6 kilometers, and then the layer above 6 to 12 kilometers, compared to CAMS, which is quite certainly a reliable kind of reference. It's not validation, but it should be quite realistic in these as a benchmark against which to compare, and then the difference retrieval versus CAMS. So we can see that although a lot of the structures are kind of reasonable, we start to see some quite fine scale structure, which is nice to see from the high spatial resolution of S5P, but there are clearly features and biases that are not perfectly handled yet by the scheme. So but we're progressing that and hope to have results from S5P in the not too distant future. Another aspect of work in CCI Plus is the addition of profile information from other spectral ranges. So this is building on other work that's been done in the National Centre for Earth Observation, where we have kind of begun to extract information from the GOEM 2 Chapuis bands, which can potentially add information near the ground because of the relatively high surface reflectance. That will become important as well for tempo. Obviously, there are great difficulties with the spectral structures in that range other than caused by ozone, like surface reflectance and instrumental features, but progress was made on that, and so we're continuing to do that in CCI+. And also a combination with thermal infrared retrievals from EASI. So as I showed, we have an EASI only retrieval, which is quite consistent with the UV, and we're starting to pull out some more information on the profile. So this is just to illustrate averaging kernels from EASI going to, and then the combination where the resolution is really kind of sharpened up in the troposphere, especially around in the upper troposphere, lower stratosphere. And then these just show some averaging kernels and cross sections across orbits, illustrating really the same point. Okay, so now I just move on to the slides provided by Catherine Wespers on the EASI retrievals that are provided as part of CCI now. So yeah, I mean, you may well, I'm sure you will be familiar with EASI. It's thermal infrared sounder providing measurements 12 kilometers spatial resolution, many spectra a day. It provides observations of ozone both day and night. Work through the CCI and in other contexts has produced quite some long-term records now from METOP A, METOP B and C that are very consistent, as well as near real-time data also processed by the same algorithm in another context. So there are lots of molecules that can be detected with EASI, as well as some aerosols as well. The ozone algorithm is uses obviously the ozone absorption band near 10 microns in a spectral range between 1025 and 1075 wave numbers. From that we get profile information can be extracted by this Pauly algorithm. The papers are there, and also the validation paper by Arno. And this illustrates the sort of vertical information or time series from the algorithm. So again, these are showing averaging kernels. There's around 4 kind of independent pieces of information that can be extracted spanning the whole profile. So in the upper stratosphere, middle stratosphere, 1 piece of information quite well located in the troposphere. And they show a nice time series from 2008 to 2017, but those records are now kind of carrying on right up to present in those 4 layers. Okay, quite a lot of lots of papers have been produced from this EASI data set. So these are kind of examples of papers that address the validation, including Arno's paper from Arno's recent paper from 2018. There's also papers. I mean, EASI is a very stable instrument and good, suited for looking at trends. So yeah, papers have been produced both on tropospheric ozone trends and in the stratosphere quite recently. So in terms of acquiring the EASI data, Catherine points you to the ARIS site, a French site, where you can kind of find most of the EASI level 2 products, including ozone. If you go in there, then you'll find you'll quickly get to this kind of page where you can find apparently two data sets. So one of them is produced via a EUMETSAT, but sort of a EUMETSAT operational processing system as part of one of the SAPs, and that starts in 2019, I believe. And then there is a data set which is produced by a consistent algorithm going all the way back to the beginning of the mission, filling up to the start of this second EUMETSAT processing. But yeah, if you have kind of questions about that, then I'm sure Catherine will obviously be able to answer better than me, and I understand she'll be online later. Okay, so that's basically all I wanted to kind of say at the moment, in giving you a quick overview of the nadir profile products.
Thank you, Richard. We have a question from Wolfgang. Please, Wolfgang.
Yeah, thanks, Richard. Have you looked at 2020 tropospheric ozone in this data? I guess it's not a data record yet.
Yeah, we don't. not in our UV nadir profile products. Well, okay, we've just finished basically processing full C3S, Yomi and GOM2B data, and we haven't really had a chance to kind of look in detail at it. We've seen we have also processed our IASI data that did kind of tend to show some 2020 in some regions having lower tropospheric ozone than in other places, but or other times.
Okay.
Which are, interestingly,
yeah,
look like it might be consistent with some other analyses that have been done. But yeah, it's early days really in terms of us kind of drawing concrete conclusions about that.
Okay.
Another question from Irina, please.
I don't bother with the camera. So that the data sets that you're showing, the tropospheric ozone data sets from different satellites you're showing, are they now different? Have they been updated with regards to what data sets been used in the TOR1 data by Audrey Gadal?
Not well. There isn't a kind of well, as I say, some of the data sets have been updated in terms of kind of extending the record. We're not yet. We're kind of working on improving the quality, so they're not radically different. Yeah, for the same time periods compared to TOR1 yet.
Yeah, I'm just curious about, we need some data sets to analyze for the tropospheric ozone trends.
Yeah, we're definitely kind of working to try and kind of do that. Yeah.
Yeah, thank you. Mm-hmm.
I mean, yeah.
Okay, thank you again. Let's continue with the next presentation. That's going to be Arnaud.
Diego, there was another question.
Just arrived.
Yeah.
Oh, sorry.
I think we still have time for a question. Yeah.
So, William, please.
Yeah, I just snuck it in there at the last second, so it wasn't there just before you closed it. But the question was sort of a follow-on from Irina's. I just want to know if there's any more information about why IASI, the two IASI products were showing different trends in the TOR report to the OMI and SCIA-Marky data. If there was any sort of update or information on that.
No, I don't have any update on that. I know there was sort of speculation about different vertical sensitivity being the reason, and/or possible. Well, yeah, I don't know. Yeah, probably it's better if Catherine kind of comments on that.
Okay, cool. I'll ask her. Thank you.
Okay, no more questions. So let's continue with Arnaud.
Do you see the slides?
Yes.
Go to slideshow. Okay, still there?
We see the two screens, so maybe you can
Okay.
change the
Then
display
I
settings.
Like this?
Now it's better.
So I show you the Ozone CCI nadir ozone profile quality assessment. This is work done within our team, essentially, at BIRA ISB. So, so the outline of the talk, I will first go through the CCI climate data records that are available and also related to the C3S level 3 records, as is clear to most users, I guess. So what goes from the level 2 CCI to the level 3 in C3S. I will discuss validation data sources and their coverage, and then our quality assessment or validation chain that consists of data content studies, information content studies, and of course ground-based comparisons. Typically coincidences within one day and within the pixel, roughly because we typically take a fixed radius to look for coincidences and not the actual pixel coordinates. We look at dependence of quality indicators on the influence quantities we consider, and then we look at the compliance of the data with user requirements as shown in the user requirement document. And then I summarize with ongoing activities and some reference documents. So this is an overview of the level 2 products within Ozone CCI, developed or continued within CCI. You see they're all products. Do you see the cursor?
No.
Yes,
we do.
Okay, so you see which products are developed by RAL and which by ULW Latmos using the Forley algorithm. And this is, so there will be, my question previously was on the GOP ECV, so there will be a level 3-like product by DLR that is merging these level 2 products. You see the data availability here in the table, and with the in purple is updated within this phase of CCI, and crosses are expected data. So you see not everything is there yet, but there's quite some material already. And so some of the available data sets are also validated within C3S, as you see in the table at the bottom. For RAL data, this is the level 3 version is created by KNMI, and you see the time ranges here. And for the YASI data, this level 3 data is created by ULB Latmos itself, but only for the 0 to 6 kilometer integrated column, which I will also show later. The data sources we are considering are typically ozone sonde data from SHADOS, WODC, NOAA, and then the match campaign from the EVDC archive, and then NDAC, of course, the NDAC ozone sonde data. For the LiDARs, we are considering stratospheric LiDAR from NDAC, also including rapid delivery stratospheric LiDAR from NDAC, and Tolnet LiDAR from the Tolnet archive directly, but also through the NDAC archive. So some are only on Tolnet, some are on NDAC. You look at the coverage of these validation data, you see the global map here. And for example, we sometimes consider comparisons within 5 latitude bands, and then you see these are divided by the green lines on the global map. But you see the global coverage is quite good. So there are about 150 ozone sonde stations and about 15 LiDAR stations. Looking first, so I will not discuss in detail the data content study, and I go to information content studies immediately, or give you some examples to show you what we are looking at. So for example, you see here time series of a latitudinal distribution of the DFS, or the number of independent layers, as the averaging kernel trace of the products from RAL, which typically, as Richard said, have a DFS around 5. For OMI, this goes towards 6 quite often. And for YASI, this is somewhat lower, as also shown in the previous presentation. But depending on the latitude, a DFS of about 3 to 4, as you can see on the map, but they have global coverage, so during day and night. If I look at the comparisons, so actually these plots combine information on comparisons. Here the RAL versus version level 2 versus the LiDAR measurements. Let me focus on the lower right plot for OMI. You see here the absolute differences, relative differences, vertical sensitivity, offset in kilometers, so the retrieval offset, and the full width half max of the averaging kernel as a function of altitude. And also the colors of the lines denote the DFS that comes with each retrieval. So for example, you see Skiamaki on the left has typically the lowest DFS, around 5. OMI is higher, but you also see that OMI often has retrievals with a low DFS, which we suggest the user could apply some kind of filtering on that is not currently done in the delivery of the product. So you see products with a low DFS have a low sensitivity above the UTLS, while a usual retrieval with a DFS around 6 has a sensitivity that continues around 1 in the stratosphere. Looking at the comparisons, relative differences here are quite similar for all 5 instruments shown here. So for the RAL retrieval, typically around 10% positive bias in the stratosphere, while the bias goes negative. You see this better from the sonde comparisons. So this is the same type of figures, but for sonde comparisons, the bias goes negative to around -30% for the troposphere. And here you see, we look at the difference in surveillance quantity. So here the colors change with the solar zenith angle of the comparisons. And you see, so for example, for the low DFS profiles, there is not really a solar zenith angle dependence, so it occurs for all solar zenith angles. So the DFS flagging, we could suggest, is easier than looking at, for example, a solar zenith angle flagging. You see that OMI somewhat differs from the other instruments retrievals by RAL, as the full tropospheric bias is negative, while the other instruments, the bias is most negative in the UTLS and then turns positive when going to the ground. If we look at the level 3 data, so as validated within C3S, the here versus SONS, we see similar behavior for GOM, Skiamaki, GOM2AB, and OMI, so all 5 RAL products. With respect to ozone sondes, note that the scale is different. So for example, here for OMI, we still see about 10% positive bias in UTLS and stratosphere and negative bias in the troposphere. And also drifts are added from the level 3 data, which are shown below. And actually no significant drifts are seen, also because the uncertainty on the measurements is quite large, as can be seen from the dispersion in the comparisons. Only for GOM2B, now we see a very significant positive drift around the UTLS and in the, let's say, upper troposphere. But this is also the shortest time series for now. So this will, the value will probably change if we look at a longer time series. Looking at the YASI data, then I focus or give an example of the YASI C retrieval in 2 versions, because part of our work within CCI was to look at the consistency between YASI A, B, and C, but also to look at the update for YASI C and YASI A, B, C between Forley versions 2015 and 2019. So if I skip back and forward, you see the same plots, same configuration as for the RAL plots, but now as a function of here DFS, thermal contrast, solar zenith angle, viewing zenith angle. And if I change between these 2 versions, you see some differences in that are due to the update of the Forley retrieval. Essentially, as I will show here, the dispersion or the uncertainty has been reduced in the UTLS. And if you look to the stratosphere or lower stratosphere here, then you can see that for version 2019, the bias has become about 10% negative, while before it was about 10% positive. So if you look at this region, I will again skip back and forth. You see that the curve switches to the other side of the zero difference line. Well, in the troposphere, the negative bias, more or less about 20% negative bias, remains for the 2 versions. Looking at the 0 to 6 kilometer integrated column for YASI, so within C3S, this is for version 2015. Actually, we see about here 1% per year or 10% per decade drift in this tropospheric column for the YASI data. While as said, the tropospheric column itself is about 20 or here up to 25% negative, has a negative bias of 20 to 25%. But here, so from the C3S data and the level 3 data, we see a negative drift of about 10% per decade, which is, as you see from the uncertainty on the drift result, which is just significantly negative. Just significant. So probably to users, these are the most interesting tables. So these conclude the level 2-3 results, validation results for RAL, and on the second slide for YASI ABC. So actually most of this has been discussed. Most general conclusions with user requirements between brackets here are about 10%, 5 to 6 DFS for RAL, with an about 10% bias in the stratosphere, and then 10 to 30% bias in the troposphere, and no significant drift for GOM and OMI, but an especially positive tropospheric drift for GOM2B for RAL. For the YASI ABC, we have 2 to 4 DFS. Again, about 10% stratospheric bias, which changes sign between these two versions, 2015 and 2019. A positive UTLS bias here and a negative tropospheric bias that is there in two versions we considered. And for the tropospheric drift, we see about minus 10% per decade in the level 3 data, while there is no or an insignificant drift above the UTLS. So there the YASI data is stable. So this is these are the major results. What we are doing in validation, so we have done a validation of level 2-3 RAL products and YASI products up to the current availability. We did an intercomparison of information content quantifiers before. We have verified YASI ABC consistency and looked at the differences between two versions that were available within CCI. Ongoing are the study of approaches for profile harmonization and smoothing difference error correction, and improvement of the level 3 validation approaches, which is not always straightforward because you also need level 3-like versions of the ground-based data, which we construct ourselves. And to come is this a full validation of the RAL upcoming GOM2C Tropomi and the YASI GOM2B joint retrieval products, a verification of the GOM2 instruments consistency, validation of the DLR merged level 3 product, so this GOP ECV, and a full validation and drift assessment of all the Ozone CCI or CCI plus final CDRs. And then some references to end with. So on the methodology, there are some papers published within CCI, latest from 2019 on the harmonization of ozone profiles or atmospheric state profiles in general. Results on the validation were mentioned by Richard. So there's on paper and my paper, both from 2018. And then of course the project deliverables, the Ozone CCI PVIR and the C3S PQAR essentially summarize the validation results or describe the validation results presented here. That's it for me. If you have any questions.
Thank you, Arno. We have some questions. Let's start with Irina. Irina, please.
Hi, finally. Yeah, you do comparisons with ozone sounds, and we now know that there is a drop-off in 2014, but it doesn't affect all stations. There is a wonderful paper by Ryan that looked into this very carefully, and there is a whole assessment that Thompson is leading with others, Herman Smith as well. So are you guys looking into this in the greater details and trying to see if this gives you the right answer, the right validation answer.
Yeah. Yes, we are indeed looking into this. We are aware of this issue, and we are looking at the stations that are affected in our validation results. First, we looked at flagging, but then depending on the results, we are further considering what to do. But we are certainly aware and looking into this, yes.
Okay, the next question is from Mark.
Yeah, hi Arno, thank you for your talk. I had a question regarding your tropospheric Yasi drift you reported. Is that of the same magnitude as the negative trends reported by Vespers et al.? Or in other words, does your drift, could your drift explain the negative trends of Vespers et al.?
But that I'm not sure about whether it can explain the trends in other works. That is to be considered together with ULB and Latmos, but I know that Anne Boinard also looked into this and also saw that there was this negative drift for the Yasi instrument. So her validation work also saw the same or a similar behavior. The effect to what extent this affects the trend studies, I have to look into with ULB and Latmos together, but this is not really done yet.
Okay, thank you.
So the next question is from Ryan.
Hi, yes, just to add to Irina's comment on the ozone sonde issue, I would just be very interested to hear if you can actually detect a drop in the tropospheric ozone in the sondes relative to some of these satellite products, because we are confident that it affects the stratosphere most strongly, but we're a little more uncertain as to what's going on. That's all.
Arno, will you comment on that?
Sorry, was it a question?
This is Ryan again. It wasn't really a question. It was just a comment added to what Irina said about the drop-off in the sondes.
Okay, yeah, thanks. Yeah, we are, as said, we are considering this, yes.
Great, thank you.
I don't see more questions in the chat. Then I would like to thank all the presenters from this first session. According to the agenda, we have now our short break. So we continue 5 minutes before 6. Thank you, everyone.